Everyone. My name is József Nagy, and I'm going to give here a training about how you can run your first OpenFOAM simulations. And if you have some questions, then please, on the right-hand side in the virtual attendee portal, post your questions to the live Q&A sessions. I already wrote notes there to post there your questions, and I'm happy to answer them. So this training is going to be in two parts, and then maybe in the middle, I'm going to answer the first set of questions, and afterwards, I will then answer the second set of questions that you have. So please post them anytime you want. Also, make sure to download in the handout session, also on the right-hand side, the training documents. It's a PDF, and then below that there is a zip file with the actual OpenFOAM case files that you can run. If you prefer now with me, I'm going to try to be slow, so some of you can follow along, or at another time in your own pace. Okay, so this is these are the things that I wanted to mention at this point. Now I'm just going to share my screen so you can see what I am doing. So if you download the training documents, the zip file, then you will end up with this zip file that you can, of course, extract. Now you can see that I'm in Windows 10, but if you are following along in Ubuntu, then you can just do the same thing. Instead of, I am using the Windows subsystem for Linux in Windows 10 to run the simulations. If you are in Ubuntu, just open up the terminal. Okay, so once you downloaded and extracted the zip file, then you are going to have to go into the folders, and there you have a video, an MP4 file, a PDF, the PDF that you can just download separately, and then there is 2D case, and then there is 3D case. Okay, so and this is now this is the material that we are going to work with today. So before I start, so the title, how to run your first simulation in OpenFOAM, may be familiar to you. I do have a YouTube channel where my very first video, I think 6 or 7 years ago, was exactly this topic: how to run your first simulation in OpenFOAM. And the first, so you may already know this tutorial, the first part of the tutorial where we will run 2D simulations, but then I'm going to bring it to another level. And we are also going to run a 3D simulation of similar geometry, and then we can compare the simulation results between 2D and 3D simulation results. Plus, back then, 6 years ago, the cases were run with OpenFOAM version 2.3.0, so a very old version. Unfortunately, on YouTube, I cannot change the videos, but now the material that you just downloaded or that you are going to download is going to be for version 2012, so the latest release of the .com version of OpenFOAM. And I'm also going to use here version 2012. So if you want to follow along, then please make sure to open up a Windows subsystem for Linux with Ubuntu in it, or if you are in Ubuntu, then just open up a terminal. And if you have no idea what Ubuntu and the Windows subsystem for Linux is, then you can just go to YouTube after this session, search for my name and OpenFOAM. You can go to my channel, and I have videos on how to install OpenFOAM in Windows 10 or in Ubuntu, and then you can just do it on your own time. Important is that if you have OpenFOAM installed, that you use the correct version. So either this is done automatically for you once you open up the terminal, or you have to just type in source and then the path to your OpenFOAM installation in etc and bashrc. So this is how you kind of load your OpenFOAM installation. You can also shorten it, but this is the command. that you need to load 2012. So now I could just type in, for example, block mesh, a command in OpenFOAM, or I could just type in simple foam and then run it. It will get an error message, but still this command is recognized by my system. This is important. If you are using a different version of OpenFOAM, possibly version 8, so the .org version, or older versions, or foam extend versions, maybe the simulations will also work for you, but I cannot guarantee because I did not test it. So the first set, also the 2D simulations may work because they have been working since 2014. So possibly you're lucky, but I cannot guarantee. For 2012, it works fine. Okay, so then let's just start. Maybe let's start with a short presentation, a short introduction of what we are going to do. So the title is how to run your first simulation of foam and also run it with a snappyHexMesh mesh. This is going to be the next level up. Okay, but let's start with the 2D simulations. This is what you can also find on YouTube. So what I want you to do, what the goal of this simulation is to understand the fluid dynamic simulation in OpenFOAM and just the basic workflow. What do you do? Why do you do it? Because I remember when I started with OpenFOAM, I downloaded it, I went to the tutorials, and then all I saw was a couple of folders and a couple of text files. And I thought to myself, okay, where do I click to open up this file? And yeah, so you don't click, you modify text files, and then in a terminal, you run an application which reads in those text files and then runs the simulation accordingly and outputs your results. And then afterwards, you can visualize your results in a separate tool called ParaView. Okay, so I want you to understand this simple OpenFOAM workflow. And where this simulation setup, how do you set up initial and boundary condition, material properties, and some rough numeric settings? How do you execute simulations and how you visualize your simulation results? So this is very simple, but the entire workflow. Okay, and here on this slide, I summarize the 5 most important steps in a typical CFD workflow. This is not just in OpenFOAM this way, this is also in commercial codes in any CFD tool. First, you define your geometry as a CAD file. Now, OpenFOAM does not come with a CAD tool, so you can use, or you have to use, a CAD tool of your choice. This can be an open source tool or any commercial code which can export STL or OBJ files. I personally like Blender, but this is my preference. On my YouTube channel, I have several videos on geometry preparation for OpenFOAM. So what we are going to do today, we will use pre-defined geometry data that I created for you, and we will only focus then on steps 2, 3, 4, and 5. So how do we create the mesh, which are small cells? What you do in CFD is that you divide up your geometry into small geometries, and then you solve the fluid dynamic equations for those small cells, and then you visualize the results. Okay, so first is to create those small cells, then you set up the physics, initial conditions, boundary conditions, material properties, and so on. And then in the 4th step, you start the simulation, and then in the end, you visualize the simulation. And here is exactly what I just told you. So in the 2D simulations, we will not waste any time with the creation of the mesh. I already pre-created the mesh for you. So this is a very special way to deal with OpenFOAM, but a legitimate way. So I created years and years ago, when I was young and I was doing my PhD, then I created in 4Fluent a couple of meshes, very simple 2D meshes, and we are going to use those for our 2D cases and import to OpenFOAM format. So we will not worry about meshing. Later on in the 3D case, we will worry a lot about meshing. Here we will import the mesh and then set up the physics initial boundary conditions and then run it and visualize the results. Okay, then let's go step by step. So what do we see here when we go into our folder here? So let's start with the 2D case. What do we see here? And this is what I try to describe also on these slides here. So if you open up any OpenFOAM case, any tutorial, what you will see are 3 subfolders called 0, constant, and system. And these are mandatory subfolders. Without those, your simulation will not work. It will crash. In 0, you define your initial and boundary conditions. In constant, you have your mesh files as well as material properties. And in system, you set up your numerics and your simulation settings. Then we have here 3 auxiliary files. So these are the fluent meshes that I created during my PhD. Actually, this elbow.msh comes with OpenFOAM, and I created the quad mesh during my PhD. And then this .foam file is for visualization later on. Okay. So this is what I wanted to tell you. Possibly, before I go into more detail regarding initial conditions and boundary conditions and so on, let's visualize this 2D mesh. How to, as I mentioned, how to create or import this mesh and how to visualize it. So we are now immediately jumping in. So what we have to now do is, if you want to follow along, then just do whatever I do here. So open up a terminal or open up your Windows subsystem for Linux and source your version 2012, and then navigate to the folder wherever you have the data that I just downloaded for you. So mine is on my C drive under workshop files, and so on. So I will just go to my C drive and my user and documents, and then workshop files, and then one subfolder below that. And here you can see that we have our 2D case, 3D case, the PDF and the video. Maybe we can quickly watch the video, what the end results will look like. So we will run 1, 2, and 3 2D simulations. And then on the right-hand side, you can see the 3D case, and we will compare them. And then we will move the results so you can nicely visualize the results. So this is what we will see, hopefully in about an hour. Okay, so very good. So now what do we do here? So usually I advise people who start with OpenFOAM to take an existing simulation case. So for example, this 2D case, and make a copy of it. So don't modify existing cases, make a copy of it and modify the copy, because this way you cannot screw up anything. And you can always have a backup. So now we can copy it in Windows, in the Explorer, or we can copy it in the terminal, as you prefer. If you are familiar with Linux commands, then you can just go ahead and type in 2D case, and I'm just going to say 2D case 3 and quad. And as you can see now, I just created 2 subfolders, but of course you can just create Control-C, Control-V, and then just rename it in Windows quad refined. So we need 3 cases. So we will leave the backup folder as it is. We will not touch it. We will just work in these 3 subfolders and run the simulations there. Okay, so we will start with the tree mesh. So this is a triangular mesh that comes with OpenFOAM. This is this elbow.msh file. So we have to now import it. For that, we have to navigate into the 2D case _try. oops, no, that's not what ls. Now we can see the contents of this tutorial case and the command that we have to execute in order to convert this elbow. Where is my mouse? Here is my mouse. This elbow.msh to OpenFOAM format is given in the PDF. It's fluent mesh to foam space elbow.msh. And what this does, this opens this elbow.msh, loads in all the data, converts it into an OpenFOAM mesh format, and then writes out the OpenFOAM command. So you can just copy it out from the PDF, or if you have a text editor, you can open up this open.foam file, and then here I put together a cheat sheet. I mean, this should also be working with just Notepad. Do I have here Notepad? Yes, so Notepad. So you can also open it up with Notepad if you don't have Notepad++. And then all you have to do is just copy the command, and then with the right mouse button, or just in Ubuntu, you can also use a Control-Shift-V to paste it. No, that's not what I wanted. Yeah, so fluent mesh to foam space elbow.msh, or you can just type it in on your own if you prefer to type. And then you press enter. So I will now leave this on the screen so you can just navigate into the subfolders if you're following along, and then all you have to do is press enter, and then I'm going to just press enter and let's see what happens. Okay, so something quickly happened here, and now it is important that here at the top we have a header, and then in this header it says version 2012. So we have the correct version of OpenFOAM loaded. If you get a message, something with fluent mesh to foam command not found, then this very first line was not executed correctly. Most probably your OpenFOAM installation is at a different location, so you have to enter your correct path. So if you have not a command not found, then you did not load your OpenFOAM correctly. But if you did, then you can just execute fluent mesh to foam, and then you will see something like this. And now we can open up the mesh. This mesh was exported in constant polymesh. These files were not there before. If you don't believe me, then I'm just going to show you here in the 2D case in the backup folder. There is no polymesh folder, whereas in the try here we do have a polymesh folder, and now we can visualize that in ParaView. So either in Windows you can just double click the open.foam file and then associate it with ParaView. So you have to download, of course, first ParaView and install it. Or alternatively, you can open up ParaView and then go to the folder. So you can just file and open and then navigate to the folder where you have your files. So I'm just going to use the lazy way, and then we have ParaView open. We don't see anything because there is this green button here which says apply. So don't forget, always click apply. This is something that you can write into your palm or on the wall behind your laptop or your screen. Always click apply if you don't see anything. Okay, so now I click apply and ta-da, here you go, there is the geometry now. So let's assess this geometry first before we progress with the initial conditions and the boundary conditions. So now it's blue because we have the pressure loaded. I just want to do a solid color, and instead of the surface, I'm going to show you the surface with edges. And this shows you the mesh. So as you can see, this 2D case is not really 2D. It is actually a 3D case with one cell over the thickness. And here you see that it is a triangular mesh. So the mesh quality is not the best, but we will improve this with subsequent cases. Okay, so the idea behind this is that we want to have a flow which enters over this face here in the positive X direction. Then a second inlet is going to be in the bottom. It's going to go up in the positive Y direction. And then here in the top, we have an outlet. And then these phases or these boundaries here and also here on the sides are walls. How to visualize that? Here you have the mesh regions, and then we can just visualize the boundaries. Apply. So we are not visualizing now the internal mesh, but just the boundaries. And now we can just click away front and back planes. These are the front and the back planes of the simulations. So these will define the direction, which is the Z direction, in which OpenFOAM does not have to solve the equations. So by defining these two together, OpenFOAM will immediately know that it only solves the equations in X and Y directions. Okay, so now what do we have here? Vol -4 is this set of of vols that just disappeared. Vol -8 is this back part. So this comes with OpenFOAM. I didn't create this, so this is how it was just defined by someone. And then you can see that velocity inlet 5 is this front velocity inlet, and velocity inlet 6 is this bottom one. And then the pressure outlet 7 is this one on the top. So now we know what is, and if I just bring back everything, I can even separate them by colors so we can identify them. Okay, so this is the mesh, and now we can open up the text files for input. Okay, so in 0, as I mentioned, we are defining the initial and boundary conditions. And depending on the problem that you want to solve, there's different number of files that you have to store. Here we are dealing with a transient, but laminar flow, so we only define the velocity and the pressure. So let me just open up the velocity because it's a rather physical quantity. So I just open it up in my Notepad++, but you should be able to open it up also in Notepad. Okay, but I would really advise you to open it up in Notepad++ because Notepad uses the Windows formatting of text files, and sometimes there's an issue with the Windows formatting of text files if you save them. So Notepad++ is a very good idea to use in Windows. In Ubuntu or any Linux version, just use the native text editor. Okay, so here we have the file called U. U is the velocity. And in each OpenFOAM dictionary, you have a header. And then you have the dimensions of that quantity. So the velocity is in meters per second. And these are the 7 SI units. So the exponents of the 7 SI units. And I wrote it here, kilograms, meter, second, Kelvin, mole, ampere, and candela. You never use or rarely use the last 3. They usually focus on the first 4. So we don't have kilogram in meters per second. So it's kilogram to the power of 0. Then we have meter to the power of 1. And then second to the power of -1. So the unit of the velocity is meters per second. So this is the dimensions entry. Then we have internal field. Now this gives for all cells an initial velocity of 0, 0, 0. So now why 3 values? Because the velocity is always a vector. And initially everything is stationary. So nothing is moving. So if I go back here, we assume in all those small triangles a velocity of 0, 0, 0. This will change with time, as you will see. Okay, later on, we will have a long list of vectors, so the values of each individual cells, but now we condense the list into one entry. This is why it says uniform. And then and this is the initial condition, and then we define the boundary conditions. And here, now you have to take care of a couple of things. First, the names here that we use have to be identical to the ones that we have in the mesh. Upper and lower case does matter. So it is important to have to watch out for upper and lower case, and also dash for, and the numbers have to be, it has to be either English, so you cannot just say it's vol 4, and then here in the initial conditions is, I don't know, in French, or in German, it's one vier. So it has to be the same exact word that you use on the mesh and here. So it's vol 4, velocity inlet 5, velocity inlet 6, pressure outlet 7, vol 8, and front and back planes in U as well as P then later on. So now let's take a look at the boundary conditions. So on the vol 4 as well as vol 8, we use the no-slip boundary condition. This is the no-slip boundary condition that the velocity is 0. So on the velocity inlet 5, which was this boundary condition, we use a velocity of 1 meters per second in the positive x direction. So this is going to be our slower inlet. And on the second inlet, we will have a velocity in the positive y direction, so in this direction, with 3 meters per second. And now this no-slip boundary condition would be nothing else than just fixed value and 0, 0, 0. So we could also just write the boundary condition like this. This will be identical to no-slip. Let me just go back here, and then we have 0 gradient on the outlet. So now what is 0 gradient? And so this is the Neumann boundary condition. So it assumes the gradient to be 0 at the outlet. And let me come to that in the pressure file. Okay, so if I just open up the pressure file in text editor, so we have the same header. We have different dimensions here. So it's meters to the power of 2 divided by second to the power of 2. Now, you might ask yourself the question, how is that the unit of pressure? Pressure is usually Pascal, and Pascal has something with kilograms. And you are correct to say that, because this pressure is not the actual physical pressure that you would expect. This is the so-called kinematic pressure. This is the pressure in Pascal divided by the density. This comes because due to the reason that the solver or the application that we will run assumes an incompressible flow. So the Navier-Stokes equations, so the fluid dynamic equations, are divided by the density. If you write down the Navier-Stokes equations and divide by the density, then in the pressure gradient term, you have to divide by the density. It does not disappear like in all the other terms. And then you have P divided by density, and you combine the pressure and divided by density into this quantity P. So this, and if you divide Pascal by kilograms per meter to the power of 3, then you end up with meters to the power of 2 divided by second to the power of 2. So this is how you end up with this dimension. So again, as initial condition, we assume the pressure to be 0. And we assume here atmospheric pressure, and then everything that we will see later on is a relative pressure relative to the atmospheric pressure. So we can have negative values and positive values. So this is not absolute pressure. And then what is important is that for the pressure, we fix the pressure to 0 at the outlet. So we assume that here we have the atmosphere where the pressure is constant. And this is important for case setup. So usually in incompressible flows, you have 2 points where you fix your values. The pressure you fix usually on the outlet, and for the velocity, then you use, for example, zero gradient. And on the inlets, you fix the velocity and you use zero gradient on those velocities, or wherever you fix your velocities. Of course, we also fix the velocities on the walls. So this is why we use zero gradient here. At outlets, there are more sophisticated boundary conditions for the velocity, like inlet outlet or pressure inlet outlet, but that's a more advanced topic. So for very simple cases, this is a legitimate case setup. Now, what is zero gradient? So it assumes the pressure gradient to be zero, but where? And now I'm just going to botch here a schematic sketch in Paint. So let's assume that this is some of our last cells, or okay, let's just create a triangle here. So let's just create here a quick triangle. Okay, so let's just say this is this triangle here, okay? So the top face is the outlet. So in CFD and in OpenFOAM, usually you take the cell center value here. Okay, now let's just use this. So the cell center value is calculated. And now the question is, what is the value on the boundary? And with the zero gradient boundary condition, you assume that here the pressure between the cell center and the outlet, so this point and this point does not change. So the pressure gradient is zero, which means that the solver just takes the cell center values and extrapolates it one-to-one onto the end. So this is what you would do for the velocity at the pressure outlet. This is what I meant with the outlet, and for the pressure on the velocity inlets. So you will do this approach here on these cells as well. So here it takes the velocity in this, the pressure in this cell center, and then it extrapolates to the inlet. Okay, so this, and one last thing is that the front and back planes are empty. And this empty boundary condition then just defines the direction in which OpenFOAM should not solve the equations. And in our case, this is the Z direction. Okay, then let's progress with the case setup. In constant, we have the mesh files. We will not take a look at them. And we have transport properties. So this is a very simple file with material properties. Here we define the kinematic viscosity of the flow. Why the kinematic? Because we solve the incompressible versions of the Navier-Stokes equation. So we divided by the density. So in the stress term, we have we don't have the dynamic viscosity, but the dynamic viscosity divided by the density. And and this gives the kinematic viscosity. And here we will use a rather high kinematic viscosity of 0.01. You can change this, you can play around with this later on as you prefer. And then in system, we have 3 mandatory files. And these are the numeric files as well as the simulation setting files. So if I open them up, so in FV solutions, you can set the tolerances and the number of corrector steps. And in FV schemes, you define the discretization schemes. Go to my YouTube channel. I have videos on these, what these mean. If that's not enough for you, you can also, of course, go to wiki.openfoam.com/tutorials, where we have approximately 100 tutorials, and there are also numeric specific tutorials, and there you can go into the depth of numerics, how to modify these 2 files in more detail. So the address is wiki.openfoam.com/tutorials. And there you can just go through all the tutorials there. Here, what I want to touch is control. So this is the control room of your simulation. Here you can set the most important settings. So what is the most important setting? This is the end time. So we start at time 0, and when do we want to stop? So here we want to stop at after 75 seconds. We have a time step size of 0.05, and we will write out every 20 time steps. So we have 0.05 time steps. So 20 times 0.05 gives 1 second. So we will have results after 1 second, 2 seconds, 3 seconds, and so on. Okay, so that's all regarding case setup. So now we can move on to the fun part, running the simulation. So hopefully you already executed this command and imported the mesh to OpenFOAM. And how you run now the actual simulation is by typing in or just copying IcoFoam. So it's lowercase I, C-O, uppercase F, and then lowercase O-A-M. So no, that's not it. IcoFoam, you can also type it in, and then you can press enter in this folder. So maybe that's also, you always execute commands in this folder where you have your zero, constant, and system subfolders. So you don't execute this command in zero, you don't execute it in constant or in system, you don't execute it in workshop files, you go into 2D case and try. And so this is the path that you have to be in, and then we can execute IcoFoam, and now the simulation is running. And this is what a typical OpenFOAM simulation looks like. So in the terminal, something is rushing by, and simulation is being run. Meanwhile, we can go back to our Explorer, and then you can see how the simulation results, the list of simulation results grow as we go. And now we reach 75, and indeed the simulation stopped. So very good. It was a very fast simulation. If we now go into this, then we can possibly open up the velocity file after 75 seconds. And now you can see that this is not uniform anymore, but we have 918 cells. And for each cell, we have a velocity vector that we can visualize in ParaView. Let's do that. So for that, we can either delete this OpenFOAM file and reload it, or we can try and refresh it with this button. Sometimes it works, sometimes it doesn't. It didn't work, so delete and then open up the open.foam file here. Click apply, always click apply, and now you can see the maximum is 75. So now we can go to a Z normal view, click this button here. And now I don't want to visualize the pressure, but I want to visualize the velocity. And now if I go to the first time step, then everything is red. Why is everything red? Because the scale is going from 0 to 10 to the power of minus 38. So it is a very low velocity number. I can rescale it with this button, rescale to data range. So now rescale to data range, if I press it, then we have a minimum and maximum value of the velocity between 0.29 and 3.2. It is a very random value, so I can also go to custom data range, and then I can just give 0 and 4 meters per second, and then we have a better range or natural range of the velocity. Okay, so for such small cases, you can even run the play button and then view it as an animation. For large meshes, for real-life geometries, the loading of the time steps would take too long, and it doesn't make sense to do this. But for this small tutorial, you can run the video. Okay, so what do we see here? So this is the simulation results. These are the simulation results here. Or velocity enters the domain with 1 meters per second, and here with 3 meters per second. Here we have a mixing area, and then it's dissipated away. But unfortunately, because we have triangles, we can see the mesh in our simulation results. We could interpolate those results with the interpolated values, which then gives somewhat better values. But so the difference between this dot and the two U's is that here ParaView interpolates between the cell center values. So this is the cell center values and this entire mesh colored by the cell center value. And here ParaView interpolates in between those cell center values, but this has nothing to do with OpenFOAM. This is purely done by ParaView. Okay, so this is the velocity, and I don't know why this changed. So 4, and the problem is that here we have, we can see kind of some crocodile teeth, and you shouldn't see the mesh in your result. So you can improve this by running a different kind of mesh, and this is why I created the quad mesh. And we can go to the second case setup by leaving this case and go to the quad tutorial, and then instead of importing the elbow.msh, we can import the elbow_quad.msh. So let's just do this. So we can go to the cheat sheet and then copy here the command, and then paste this. Again, copy the command and paste it. And if we execute this, then this will not load elbow.msh just before, but the other Fluent mesh, and import it as an OpenFOAM mesh into constant polymesh, if you remember. So now I press enter. So now something happened. And now all we have to do is run the simulation, because we didn't change anything in the case setup. I just showed you what the files are, what the settings are. We will use the same settings. The only thing that we changed here is the mesh, the type of the mesh. So I will just paste icofoam and press enter. And now the simulation runs. And let's wait until the simulation finishes. And then we can take a look at both simulations side by side. So because I just saw that you don't have any questions, if you have any questions, just post them in the discussion forum, and I'm happy to answer them after we finish with the 2D simulations. And then before we progress to the 3D, I'm happy to answer your questions. Okay, so in the meanwhile, the quad mesh finished. So now we can just open it up. So maybe I just call this tree mesh, the triangular mesh, and then I just go one up into quad, and then open up the open.foam file here. Always click apply. And now what do we see here is that they are not on top of each other, and it's a bit shifted. And I did it on a purpose so I can show you some functionalities of ParaView. So first I will just rename it to quad. You can just click it, and then you can just change the name and then change this to the velocity. And now you can see it is similar, but not the same. So there are some differences between the tree and the quad mesh. And let me just show you the quad. What I mean by quad, it's a quadratic mesh, fully quadratic mesh. We don't have any triangles here. And so the mesh changes the results. We don't have any teeth. We don't really see the mesh anymore in our results. So this is better. Okay, so now how do you move now around? So first you can, first you have to click this gear button, the toggle advanced properties, in order to enable more settings in ParaView. If you have not done so already, then click this, and then you can go down here to transforming. And then with the translation option, you can move around, for example, now the quad mesh. And in order to have whatever we had in the video. So first was, I believe, the tree mesh on the left-hand side, and then the second was the quad mesh. So we have to move it in the positive X direction and the positive Y direction. So I never know what this value is. I remember that it is a rather large value. So I believe 75, no. Then 125, that's a bit too much. 105, that's possibly okay. And let's just say 35, no, 30, 30, that looks good. Okay, so now let's bring it in the center. And one last thing that we can do, we can go all the way to the bottom here and enable parallel projection. And now we can really see a planar view of both of them. So this is the tree mesh and this is the quad mesh. Okay, so I enabled parallel projection, and then if you missed it, I moved the quad mesh by 105 and 30 meters in the positive X and Y direction. So this is a tutorial case. It's a huge geometry, but it's really about understanding the workflow. Zero, constant, and system, executing what are the different files and how to treat them. Okay, so this is the quad mesh. And then let's do the same for the refined quad mesh. So 2D case, quad, and refined. And if I go back to the cheat sheet, then we can just copy the commands, fluent mesh to foam. And then in this case, we will import the same quad mesh. And now we will execute refine mesh space minus override. So up until now, we did the same as before with the quad mesh, but now we will refine the mesh once. So we will cut through the center in the X and Y direction. So we will have 4 times number of cells. And now we can run icofoam because we have now more cells. This will take a bit longer, but oh well, we can then immediately load the results here on the right-hand side, and then we will have 3 simulation results of the triangular mesh, of the quadratic mesh, and the refined quadratic mesh. Okay, so it takes a while. Quad here, so we are at 14 seconds. And as I can see, there are no questions. So I am so clear that most probably you already saw this video on YouTube, so you know what I'm doing here. This is why there are no questions. Okay, so we are at 25. Maybe I show you that we can also load in just intermediate results, quad mesh, open.foam file. So this is now the refined quad mesh. So again, it is moved. So I will just move it by, I don't know, 2. No, that's too much. 180, that's okay, and 30. And then let's visualize the velocity. Okay, and now in order to compare these 2 meshes, quad and quad refined, you can see that this is indeed a finer mesh than the one here. And now currently we are at a time of 56. So we can now refresh simulation results, and then we can go to 51. And then at that time, these results still change, but then here at 60, they're stuck because we don't have the results at 60 seconds. So this is the reason why, but soon we will have it. We are at 71, 72, 3, 4, and 5, and now the simulation finished. And now I can just refresh it and go until the very last time step. And now what we just did in the video and also on YouTube, we can now watch the velocity on the 3 meshes. And now you can see the difference and the influence of the mesh. So a very bad quality mesh can diffuse your simulation results. With a quadratic mesh, or the difference in 3D is that you should avoid tetrahedra or prisms and use predominantly hexahedra. And the finer your mesh is, the better. So as you can see here, it's not so diffuse as in these two cases. And indeed, in this case, we even depict a small backflow region. Here, as well as here, we can assume that also in this simulation, but here with the triangular mesh, this backflow region is completely gone due to the mesh quality. Okay, so this is what you can also see on YouTube. Now we are going to bring this to another level. And I mentioned that I'm going to answer your questions at this point, but since there are no questions, then let's just go ahead. So here you can see exactly what I mentioned, what I already talked about. So I'm not going to repeat myself here. Now let's progress to the 3D case. And here, I don't want to concentrate so much on the case setup because I already explained it for the 2D case. I want to concentrate on the mesh. It's exactly the same regarding the initial conditions and boundary conditions for a 3D case, except here you don't have the empty boundary condition, so no 2D boundary condition, and also the material properties and the entries in system are the same. Here we need a mesh. We don't have any mesh. So here we will now, in the next approximately 40 minutes, create a 3D mesh of this elbow case with snappyHexMesh. With the automated mesher of snappyHexMesh, I pre-created a geometry for you, and we will run the mesher, and then, of course, we will also run the simulation and visualize the results in ParaView. Okay, so this is the workflow that I showed you before. So the first step is already done for you. I already created the geometry. It can be found in the 3D case in the geometry folder. So it's 4 STL files, the 2 inlets, 1 outlet, and here I use only 1 wall. I did not separate it like in the 2D cases. Then in the second step, we will create the small volumes, the mesh, where OpenFOAM solves the equations on, and then we will run the simulation. Okay. So for the meshing, we need couple of additional dictionaries, and this is called snappyHexMesh dictionary and 2 additional dictionaries, surface feature extract as well as block mesh. What are those? So now I try to explain the basic idea behind snappyHexMesh and how it works. So as an input, snappyHexMesh requires a set of STL files or surface mesh files. So it can be also an OBJ file, but usually you use an STL file. And so you can see here the red, the orange, the green, and the gray files are shown here. I can, of course, open them up for you in ParaView. So for example, this is the wall, and then you believe that this is the inlet, outlet, and then inlet 2. So this is what the 3D case will look like. And then snappyHexMesh does an optional step where we extract sharp edges. And this is very important for simulations where you want to use sharp edges. For example, if you have a flow detachment, there are sharp edges are important. And with this intermediate step, you can extract those edges, and then you can define at those edges, use a different refinement with snappyHexMesh along those edges. And so you create these features. So you have input of the STL files, you have the input of the edges, which we call features, and then we have a third input, which is called block mesh. And this is really a bounding box, a starting mesh, a block that is set up by a rather coarse mesh, as you can see here. And then what snappyHexMesh does, it loads in the geometry as well as this initial mesh, and then it refines the initial mesh around our geometry. So in the first snappyHexMesh stage, it takes the STL files as well as the edges and refines the mesh where the STL files cut through. So you can see that it takes the cells. It takes here, for example, this cell, it cuts through the X, Y, and Z direction, and then you end up instead of 1 cell with 8 cells. And you can enter the level of refinement. So you can do this once, or you can do this twice, as many times as you want. And then you define a point inside of the geometry, and then Snappy will throw out everything that is outside of the geometry, and then you end up with a mesh like this. I call this Lego mesh because it looks like we build up the mesh out of Lego bricks. And then snappyHexMesh in a second stage then snaps, so moves the nodes close to the STL surface. So this is now the difference between the first stage and the second stage of snappyHexMesh. And with this, in snappyHexMesh, you can automatically create curved surfaces. And this is very important for real-life geometry. And then we can run the simulations. Now, okay, so this is the basic idea, that we need 3 inputs: the STL files, the edges, and the initial block, and then we can run snappyHexMesh. Okay, so then let's just go into mesh. So I'm just going to create a mesh in this subfolder called mesh, and then copy the mesh into the case folder. You can do it everything in one folder if you prefer. Okay, so what do we do here? So again, a cheat sheet is shown in this open.foam file. So the commands that we execute is we copy the STL files from the geometry folder and we paste it into constant tri-surface. Here, why in constant tri-surface? This is hard-coded in OpenFOAM that I cannot change. So I will just copy this command and then paste it. Okay, I have to change the directory. Not even that, I will make a copy of the 3D case, just as I mentioned, we should. And 3D case workshop, I don't know, 3D case snappy. Let's call it 3D case snappy. Let's go into 3D case snappy. And then we have here case, geometry, and mesh. So in geometry, we have the STL files. In mesh, we will create the mesh. And in case, we will run the simulation. Okay, so I will go into the mesh folder. I will now really copy and paste this command. This copies now the STL files into constant tri-surface. And now, first we extrude the edges with surface feature extract. And now what we have here is in mesh constant, we have an extended feature edge mesh. As well as here in tri-surface, we don't only have the STL files, but also so-called eMesh files. And in here, we have some object files for visualization purposes. So these eMesh files are the edge files that are used as an input for the edges. So here we have the STL files and the edge mesh files. We did not create the block mesh yet. So for that, we need 3 text files: block mesh dictionary, snappyHexMesh dictionary, and surface feature extract dict. And surface feature extract dict defines exactly these previous steps with surface feature extract, which STL files should be taken and the edges extruded. So inlet 1, inlet 2, outlet, and wall. So if you change your geometry, you have other STL files, just copy paste these entries, just change the name of the STL. Fine. Then in block mesh dictionary, now we define our initial block. And here the 2 important entries are these 8 coordinates. These are the 8 coordinates of the block, or so the nodes of the block. You can change this. So this is really the bounding box around the STL files. So if you have different STL files, you have to modify these entries. And then these 3 numbers. So this is the initial mesh refinement in X, Y, and Z direction. And I'm not sure why I have here 8 in the Z direction, but let's take a look. Okay, let's take a look at the number of cells here. So we execute here block mesh. And what do we have here? So let's just open up the mesh. Okay. I'm in the wrong folder, sorry. So 3D case snappy, mesh, and open.foam. And now you can see that here we have a mesh that is around this. So this is really the bounding box of around the wall, and also the inlets and outlets. Usually it is a good idea to make it a bit bigger than the geometry. And now I also remember why I put it here 8 cells, because here this 2-cell approach was a very, very coarse approach. So let's just roll with 8 cells here. So this is our initial mesh, and now we will refine this exact initial mesh with snappyHexMesh. How to do that? And now we can, let's just execute snappyHexMesh minus override. And now snappyHexMesh is running. So it was very fast. And what happened here? So first, let's go to the very top here. So, okay, so we now execute block mesh. We created this block here, and then we execute snappyHexMesh minus override. Then what is happening here, it loads the emesh file. So as I mentioned, those edge files, inlet 1, inlet 2, outlet, and wall. And it loads in also the STL files, inlet 1, 2, outlet, and wall. And then it starts with the refinement phase. So feature refinement, it looks for those edges and then refines around those edges. So there was nothing to refine, as it seems. And then surface refinement 0. So it looks for the STL files and then refines. There was nothing to refine. So it skipped all the cells, and then we ended up with 6,000 cells. Now, why didn't it refine? And for that, we go into snappyHexMesh, and because we didn't specify anything yet. Okay, so there are 5 steps in snappyHexMesh. It can be very overwhelming, but really it is 5 steps that you have to take care of in snappyHexMesh in order to run the meshing. First, you have to make sure which stages you want to use from snappyHexMesh. First, the castellated mesh stage is really the case where we refine everything and we end up with the Lego mesh. Then the second snapping stage is where you bring the faces close to the STL files, and you have then the nice curved surfaces. And additionally, you could add layers, but this is a difficult task, so it's nothing for this tutorial. So usually you would enable the first 2, and then if you want, then you can use layers, but you will always use these 2 and so set it to true. Then the second step is to load the STL files. And there is a certain syntax how you do it. So this is what you do it. So first, in geometry, you define the name of the STL file, then it's a type tri-surface, and then you want it to be called inlet 1. So we use the same name. If you have some cryptic name from your CAD, then here you can redefine the name to a more more natural name. So, but an inlet 1 is fine. So this is why I use inlet 1, inlet 2, outlet, and also wall. So now we can define certain refinements. The third step is to define the refinement along the edges. So these are the emesh files. And as you can see, we did not refine at all. This is why it skipped those stages in snappyHexMesh. So maybe we could define level 1, possibly. The fourth step is then the refinement along the STL files. So inlet 1, 2, 3, 4. And here you have the possibility to use a minimum and a maximum value. So, and then internally, according to an algorithm, snappyHexMesh decides which, so we could now just write 1 and 2. And an algorithm in snappyHexMesh decides whether to use level, to refine once or whether to refine twice. Of course, you can use any numbers, but don't forget that the higher the number of refinement, the higher the number of cells is going to be. And also the simulations will be very slow. Plus, if this is too high, then you may be outrun your RAM on your laptop or your PC. So watch out for too high levels. Okay, so but I want to use level 1 here in this tutorial for everything. And then the 5th step is to find the inside point of your geometry. And there is a very short trick how you can do this. All you have to do is load your geometry and then move here to the very bottom, change the background color to black, and then go here, just click on the STL file and go here to probe location. Then you have here this cross, and then you can just drag it and move it, and then move it somewhere inside of the STL file. And then you can use these values as location in values. Just copy them and then paste them here. So okay, let's just use here 0, -22, and 0. Let's see where this is. 0, -22, and 0. So this is actually also inside. So this is fine. So if we want to mesh the outside, so we want to run a simulation around this elbow, then we would put it outside, and then the mesh inside of the geometry would be thrown away. This way, we will keep the meshes inside and throw out everything that is outside. Okay. Okay, so this is the last thing. And now I believe, no, I don't want to have this probe location here. And now I do want to refresh here and then see what happens. So with level 0, 0, 0, we have a nice mesh, but as you can see, this inlet is not coarse enough. So this is why I set it up this way. Now, if we want to rerun Snappy, then that is also here. So all you have to do is delete the mesh. No, delete the mesh, run block mesh, and run snappyHexMesh. And why don't we have to do the extraction? Because those eMesh files did not change. Okay, so now we can go back to the beginning here. So we load the eMesh, the STL files, eMesh files, and then we go into the refinement phase, and we did not save. Okay, so don't forget to save. This is a typical thing that can happen. So I'm just going to use my cursor keys again, delete the mesh, block mesh, and snappyHexMesh. And now now you can see it takes a bit longer. So we can just go up here. Okay, so now we have here refinement phase. The features, 82 cells are found, which have to be refined along edges. And then in the second step, only 15. Then 5 more cells have to be refined, 2 more cells. And then in the 4th iteration, none of the cells. And then this way, we started with 10,000 cells, did we? So we had 9,500 cells. And then after refining only around the edges, we ended up with 10,200 cells. Just a small increase in number of cells. But now we come to the STL files. And now defining by the STL files, we refine in addition in 2,000 cells, then 17 and 0, and then a second shell refinement step. And then we end up with 38,000 cells. And then we will look for the, or snappyHexMesh looks for the location in mesh. and then this decides what to throw away. So we have 38,000, but here we also have the outside cells. And then somewhere here, yeah, location. Here we have location in mesh. And then it at some point throws away, remove unreachable sections of the mesh regarding this point. And then we move from 38,000 to 21,000 cells. And then, yes, so 21,000 is what we end up with. And then we write the mesh of the first step. And then we go into the second snapping stage where we move the cells closer to the STL files. So this is really what all this fuss is about. And then in the end, yeah, so it finished without any errors, luckily, and we have 21,000 cells, but now we should have a finer mesh. So I want to refresh here, and now you can see that we have a finer mesh. Here the inlet is not the best, but oh well. You can go to level 2 and then run this, but now I want to go to the simulation part and how to do this. We can now rotate the geometry or scale it if we want, but we will just, since this is the correct size, we will just take the mesh as it is and then copy it to the case folder. Okay, so how to do this? For that, we go into the case folder here, and I just open up in the case folder my my cheat sheet here, and I copy the mesh from where we just created it, from constant polymesh, and I copy it into my case. So I will take here from mesh constant this folder to case constant and paste it here. Okay, so copy mesh constant polymesh to case constant, and now as you can see, it just magically appeared, and now everything is set up correctly, so we can just double check it if you want. So in the pressure, the outlet, the pressure is 0 and everything is 0 gradient. Again, we don't have the front and back planes in this case because we have a fully 3D simulation. And again, at the outlet for the velocity, we use 0 gradient, and we use the same velocities at the first and the second inlet. And then we use the same viscosity for the material, and we use the same simulation settings. So we will run this until 75 seconds. We do need a smaller time step because it's a 3D case. So we, instead of, it's really 40 time steps here. And so we still save at every second, but we have a smaller time step size. Okay, so now we can just type in icofoam, and now this 3D simulation is running. Of course, we have now 21,000 instead of a couple of thousand cells, so the simulation takes a bit longer, but now we did the simulations for the 2D case of the triangular mesh, the 2D case of the quadratic mesh, and the 2D case for the refined quadratic mesh, and we are currently running the 3D case. So this is how you set up a 3D case. So I know that this is a bit overwhelming and fast, but just go through the slides on your own pace and just open up the cheat sheet in open.foam. In the open.foam files, there you have all the commands that you require. You just execute it, open up the text files, and then I tried to comment the entries so you know what's happening there. And also, if you want to know more regarding meshing, then here I have further information. So on the openfoamwiki.net, you will find a set of slides from the 7th OpenFOAM workshop by Andrew Jackson, which is If you click on it, okay, so this is now my other screen. So just click on it, and it is a very long 74 slides of explanation of snappyHexMesh settings. And also now there is a very good official documentation of snappyHexMesh, so you can also click that link in order to learn more about snappyHexMesh. I just showed you the basics, the 5 most important settings in snappyHexMesh, plus surface feature extract and plus block mesh. But if you want to know more, just here are the references in my slides. Yeah, so that's really it. So we are currently running the simulation. We are at 31 seconds. So actually we could load the simulation results, the 3D, and then just move it around in ParaView and then visualize all the 4 simulation results. So let's just go to 3D case snappy, and in case I'm just going to open up the open.foam file, always click apply. And now here is our geometry. So let's just move. No, okay, so now this is a 3D case. So I want to put a slice through the center. So we have the same view as with the 2D cases. So I want to put a Z normal slice. So here I pressed this button, this slice, and I want to put a Z normal slice. I do not want to show the plane, and click apply. And now I'm going to move this slice and not the origin, the full 3D mesh. I'm going to move the slide, or not slide, slice. So let's see what's the best. So 210 is not good. It's not enough. 240 is not enough. 250 is not enough. Okay, 260. And then move it up by 30. Okay, so now we have the same position. Of course, we do not have the results at 75, but we did have it at around 30. And now you can see, yeah, so now you can see that it is a similar flow, but don't forget that these 3 are planar 2D cases. So you don't have a circular inlet, but rather a very, very long inlets. So yeah, this is what the 2D case is, and the 3D case is similar but not the same. So just something to keep in mind. So yeah, so we are not now at 63 seconds. So I can refresh it, and then I can run this until 60 seconds. Yeah, and now we have to wait a bit until we reach 75 seconds, and then we can visualize all the results. And then I'm going to show you how you can export screenshots and how you can export video, for example. Okay, so we are at 72 seconds. We're almost there. So even with this finer mesh, simulation finishes within 5 minutes on a laptop in Windows 10. So it's a fast simulation. So you feel free to go for level 2 in your snappyHexMesh the settings and test what happens if you refine the mesh even further. Okay, so now, so this is now the 3D case, and I'm just going to refresh the 3D case, zoom in and out. That helps usually. And now here we see the differences between the triangular case, the quadratic case, the refined quadratic case, and the 3D case. We can even do something cool and, for example, annotate with a text. So I'm just going to write here tree. This will write here tree. I will position it to go here below it, and then go up. Okay, let's just use 0.8 here. And then I want to write quad, refined quad, and 3D. What does this look like? Not very good. So let's just add a couple of spaces here. Oh no. Okay. So that's decent. I believe that should, oh no, so refined quad, okay. Okay, that looks better. Okay, so now I hope that you can see that this is the triangular case, quadratic, refined quad, and the 3D case. And then maybe we can even add in the time source. That's also always a nice addition to have. You can add a lot of things, but what I want to show you is how to export a screenshot. So you can export, so you can go here to File, Save Screenshot, and then wherever you want to do in workshop files, you can create a new post-processing folder. No post-processing, okay. Well, and then picture, and then we can put it to full HD, press OK, and now we should have here a post-processing folder, and then we have our, okay, this is all wrong. So, so the best way is to use the predefined resolution, because then this is better. But you can just define 3 quad in different texts, and then it will scale correctly. And then how to export an animation? You can do this by pressing Save Animation. And then animation, you can export a set of PNG files, for example, or you can directly export it as an AVI file. Usually, you don't do this. Usually what I do is export a set of PNG files and then combine them with FFmpeg. So let me just show you also this possibility, animation, and then not the AVI file, but a set of PNGs. Okay. Good. So, and then actually, this video is exactly how I ended up with this video. So I took this set of animation PNGs and then combined them into a video. Okay, so let's see whether this animation AVI file works. No, of course, the Windows player doesn't work, but maybe VLC. Yes, VLC always works. Okay, yeah, so the problem with the AVI file is that the frame rate is off sometimes. So yeah, so you can play around with the frame rate. Yeah, I personally usually use this approach to export all the PNG files and then combine them with FFmpeg. If we really want to do a short FFmpeg tutorial, then the command is FFmpeg and then -R, and let's say frame rate of 10, then input anim dot 00, and then so, and then percent, and then how 02, because we have here 2 numbers, and d dot png. I usually use -b colon v, and then a very high number, and then video.mp4, and then this creates now a decently formatted, yeah, video. So this is how you can export videos from ParaView. You can play around with the settings, with the text, with the position of the geometries of the meshes, but that's up to you to find out how. Okay, so we have 5 more minutes. So maybe we recapitulate, so first we started with the 2D cases, and I showed you the case setup of a usual OpenFOAM simulation. Maybe I show you it in case of the 3D. So it's all the same. 3D case. So you have 0, constant, and system. In 0, you have your initial conditions. In constant, you have your mesh files and your material properties. And in system, you have your simulation settings. In 0, depending on the physics that you want to solve, you have 2 or more files. You have to watch out which one you need for individual solvers. But you can learn about this on my YouTube channel or in other trainings in the workshop. Then here you can define your viscosity, and then in control dict you can change your end time. Then here in the 2D cases, we imported the mesh from Fluent format, and we just ran the simulation just to have a first simulation results. What you usually do is create the geometry. I pre-created this geometry in form of STL files for you. So you do that in your CAD tool of your choice. Then you create your mesh by setting up a set of input files, STL files. Then you extract the the edge mesh files, the eMesh files as input, and then you create a block mesh, your initial mesh, and then you start snappyHexMesh, which then refines the mesh around your edges and your surfaces, and then it snaps the Lego mesh to your STL files to have a smooth surface. And then you can take the polymesh folder and then use in any of your simulation case that you want, and then place it in constant always. And then you can run the simulation. We use the icofoam folder, which is a very simple solver for laminar transient flows, but you can just, the mesh creation is the same, whether you're using a steady state simulation or a transient turbulent simulation or a combustion simulation, multi-phase simulation. The meshing stage is always the same, and you place it always into constant in your simulation folder. The only difference is the number of files in your 0 folder here, and also the number of files in your constant folder. If you have more involved physics. Okay, so now the session is going to end in less than 2 minutes. I do not see any questions. So I assume that either I was too fast or everything was clear. So I assume the first. So I hope that you still could follow along and understood the basics, and that maybe at a later point you can go through these case files in your own pace. As I mentioned, go through the PDF, open the open.foam files, which you can use to open up the results in ParaView. But you can, I also use them because they are empty text files. I usually like to use them as cheat sheets for the commands. So you just open up in a text editor, and then you can just copy paste the commands, and then you can just take a look at each individual steps that we did. Okay, so the session is about to end. So this is what I wanted to show you. So with that, I would like to thank you for watching and listening, and I hope to see you somewhere at the workshop. So thank you and bye.